Hello, good afternoon or good evening, depending on when you are listening to this video. This video was this lecture was supposed to have been done last week, but due to technical challenges, we had to uh, postpone the lecture. So I decided to record this video. It is good for you because you can listen to the video several times, as the number of times that you want. You can pause, you can skip some sections. But once again, I apologize for last week. I know many of you had bought bundles for that lecture, but it could not just take place. So this is lecture number 2. We have already had one, so this is just a continuation of the last week's lecture. So today's lecture is basically going to be on electric fields, or basically electric potential and electric potential energy. These are terms that we shall repeat several times, and I'm going to explain in details the difference between electric potential and what we call potential energy. So the lecture is divided into several sections, as you can see on your screen. I'm going to give you an introduction, and here basically is where we're going to give you some difference between electric potential and potential energy. Then we'll look at what we know as a potential difference, and then we shall go deep into the electric potential, which is our core sub area in this lecture. Then we will also look at the connection between electric field intensity, that is given the symbol E, and electric potential, that is given the symbol V. Then we shall look at some numerical examples of how you can apply some of the expressions that we will meet in this lecture. I think then after that I might give you some exercise for you. So first and foremost, this lecture, it's good to try to remind ourselves of what we did in a previous lecture. If you can recall, in the previous lecture we had looked at what we call the Coulomb's law. We define how the forces behave between charged particles, and what happens with the distance between the charged particles. Does the force increase or does the force decrease, depending on whether the distance is made bigger or made smaller? So the first bit of this lecture is just an introduction, which I'm calling here a warm-up. So I remember before the last lecture aborted, I had given you this question for you to try, and at that time I had not shown you the solution. So here I'm going to explain how it is done, and then maybe you can also verify the answers using your calculators. So this question goes like this. You have 2 point charges. One is 3 microcoulombs and the other one is -9 microcoulombs. They are separated by a distance of 20 centimeters. Then a 7 microcoulomb charge is placed midway between these two charges. So the question is, what is the magnitude and direction of the electric force acting on this charge because of the other two charges? So a better way in which you can handle such a question, first of all, is to have some sketch of how you understand the question. First of all, you are told that there are two charges. So you can just put some points, call one Q1, call the other one Q2. So those are the charges. and then the distance between the charges is 20 centimeters. Then the third charge is brought in the middle. So in your sketch, you call that one Q3, you put it at the center. That means it will divide the total distance into two halves, 10 centimeters each, or 0.1 meters. So that is the sketch according to what the question has said. Then you now come to the technical bit. For example, the charge Q1 is positive, charge Q2 is negative. You are bringing a third charge in the middle, which is positive. So this question, you do it in bits. Remember, Coulomb's law deals with forces between two charges. So you take two charges at a time at the center. I mean, you take the center charge with the Q1, you get the force. Then you take the center charge again with Q2. So you take those two scenarios. So you calculate those two forces. Then once you have the magnitude, depending on the direction, it will tell you whether you need to add or subtract or do whatever kind of operation for you to get the resultant force. But now let's look at now the signs of these charges. Q1 is positive. Q3 is positive. We expect that Q3 will be repelled by Q1 because they are like charges. So I decided to use the red color to show the direction of the force in which Q3 will move as a result of being brought near Q1. So because Q3 is positive, Q1 is positive, you expect it to be repelled, to move away from Q1. So that's why you see the red arrow. Now you put that aside. Then you come to Q3 and Q2. Q3 is positive and Q2 is negative. You expect that Q3 will be attracted to Q2. So I've used a green color to show the direction of Q3 as a result of the charge Q2. So now that you will have calculated the magnitude of the two forces, because force is a vector quantity, that means how you add them depends on the direction. So these two forces, the red and the green arrows, they are pointing in the same direction and they are parallel. So that means the resultant force is the sum. That means you just add whatever value you get for the Q1, Q3, you add to the other value that you get between Q3 and Q2. So when you sketch it like this with the arrows, you don't need to struggle to know how to get the resultant force. This is a straightforward question because the three charges are in one straight line. Ordinarily, if you are dealing with a situation where the charges are not in a straight line, then you need to be very careful on how you calculate your resultant force, because it will not always be addition or subtraction. I mentioned last week that sometimes you might need to use Pythagoras theorem. Sometimes you might also need to use the parallelogram rule to get your resultant. So this question was a straightforward one, and I think you can do it and get me an answer. So this is just part of what I've explained already, that F1 is repulsive, that is between Q3 and Q1. F2 is attractive, that is Q3 and Q2. And then the arrows of the two forces will tell you how to add or subtract. So in this solution here, we have said that since the two forces are parallel and pointing in the same direction, those are two important things: parallel and pointing in the same direction. The resultant is the sum of the two forces and is pointing in the same direction. Yeah. So when you have two forces pointing same direction, the resultant must point in that particular direction. But if the two forces are, for example, if the two forces were facing opposite directions, then obviously the resultant would not be an addition. The resultant would be obtained using subtraction, and the direction would depend on the magnitude of F1 and F2. Okay, so maybe you can get a question dealing with the resultant with the opposite direction of forces, and please take care of that. So you proceed. Once you get the two forces, then you add, okay, use the Coulomb's law to get F1 and F2, then you add. Remember the distance between the charges is 0.1. So you proceed and you get your final answer. Okay, so the answer is not indicated, but I expect you to get an answer. So if you, whatever answer you get, if you want to confirm whether you're right or wrong, please, you know how to get in touch. Do that and let me get, a feedback of how you have done this warm-up question. So let's go into a little bit of the main topic of today. So first and foremost, we want to get the understanding of what is electric potential, which is given by the symbol V, and potential energy given by the symbol U. So the first thing that we say is that in order to move a charge from one point in an electric field to another, work must be done on the charge. That is more like common sense, because when you have distance involved and you have force, then obviously work done is the product of force and distance. So if you have to move a charge in an electric field, okay, so in an electric field simply means that the force can be in the opposite direction to the electric field intensity. In that case, the work done becomes negative. And if the force and field intensity are in the same direction, then you expect the potential difference to be positive. So what am I trying to say is that the work done in moving a charge from one point to another is equivalent to the potential energy. Okay, so the work done is equivalent to the potential energy, but the position that the charge takes, or the location of the charge, is obtained or is given by what we call the potential. When the charge is just at a fixed position within the electric field, we say that particular point has an electric potential, which can be calculated. So when it moves from one point to the other, it moves between 2 points that have different electric potential. Let me explain. This point number 3 here, the concept is analogous to that of gravitational potential. We have done some mechanics in our previous unit, but let me just remind you that when you take a piece of wood, for example, you put it on top of a table. Normally, we say that the wood has potential energy, because when you simply push it, it will do some work, it will fall to the ground. So when it is on top of the table, it has some potential. That means it has an ability to do work. So By virtue of the position in which the object takes, we say that position gives it a potential. That is what we call it, that is what happens in the gravitational scenario. In the electric scenario, it is the same thing, only that now we are not talking about a table, but the position that a charge takes means that position has an electric potential, which is V. And when it moves from one point to another, then you can get what we call a potential difference. But the work done, if you consider the force that is used to drag the charge from one point to another, then that work done is equivalent to the potential energy. All right, so these two terms sometimes are confusing. I am saying there is an electric potential which is measured by volts, and then we have potential energy which is measured in joules. Potential energy is basically the work done on moving the charge from one point to another. Within the electric field, there are different points. Each point is characterized by an electric potential. That means the voltage at different points is not the same. That is what we call electric potential. Now, potential difference, just like I've explained, that one point has a potential different from another point, which also has a potential. So the difference between 2 points, if a charge moves between 2 points, the potential at those 2 points, the difference in potential between those 2 points is what we call the potential difference. That's why we're saying if 2 points have different electric potential, then the potential energy of a charge changes as a result of moving from one point to the other. The potential is a property of the field. The potential energy depends on both the field and the size of the charge. So we expect that when we come to calculating the potential energy, we shall involve the electric field intensity and the charge Q. Whereas the potential is just measured in volts. It is simply dependent on the electric field. It doesn't depend on the charge. It just depends on the electric field. The potential at a point in electric field is defined as being numerically equal to the work done in bringing a unit positive charge from infinity to that point. Electric potential is a scalar quantity and is measured in volts. Based on this definition, the potential at infinity is 0. So basically the word infinity here means that when you have charge that is some distance where electric forces are not felt, that is basically what we call infinity. So when you have a charge that is not near the electric field, we say it's at infinity, and the potential at infinity is 0. Okay, we shall get into that. Now, there's a diagram here. We have 2 charges. We have a point charge, which is at position A, and we have what we call a test charge, which is at position B. The distance between the 2 charges is x. So our point charge is Q, our test charge is Q prime. Now, here this is what we say. The point charge at A exerts a repulsive force F on the charge at B, where From Coulomb's law, we have the formula F is equal to K, the product of the charges, divided by the distance squared. That is the Coulomb's law. And we defined that K is a constant which has a value, but you can as well obtain it through the formula 1 over 4 pi epsilon naught. We said epsilon naught is used when the medium is air or vacuum. All right. So the equation number 1 is straightforward, Coulomb's law. If the charge at B is moved by some external agent through a small distance delta x towards A, where delta x is too small that F can be considered constant. Now, let me explain why the condition for using delta x. Normally, when you want to derive an equation, you first of all take some very small quantities. If it is distance, you take a very small distance, and then you now elaborate it or integrate it to obtain the whole picture. So we are saying that the charge at B is moved towards A, all right? So it is like forcing it, because remember, A is positive, B is positive. So when you bring B towards A, it simply means you are moving it against the electric force, because they are supposed to be repelling, but you are going against the repulsive force. So because of that, the work done will have a negative sign, because the direction of the displacement and the direction of the force are opposite each other. So if the distance is delta x and the force involved is F, then the work done is the product of F and the small distance. The negative sign I've explained, it is because the displacement direction of movement and the direction of the force are opposite. Remember, displacement is a vector quantity, force is a vector quantity. So the two are in opposite direction, and that's why you have the negative. So equation number 2 will help us in the next part. Now, if we substitute F, for F, remember, let me go back to equation number 2. Equation number 2 is force, negative force times delta x. So we want to substitute for F from the Coulomb's law. And if we do that, F alone is 1 over 4 pi epsilon naught, product of the charges over the distance squared, then multiplied by delta x. We get equation number 3. The total work done, if you want to get now the total work done, the operation that you are required to do is an integration, because you have begun with small quantities. Now you want to get for the whole picture, so you have to do an integration. And if you do that, you integrate with respect to x, because x is the variable and the distance is, you are moving it from infinity to some distance r around the electric field, from infinity where the forces were not felt to some distance r near the electric field. So you just carry out the normal integration. You know how to integrate 1 over x squared. You do that, and then you substitute infinity and r. Remember, the negative will still be there because of the infinity. You will just carry it out properly, and when you substitute infinity, you will find that equation number 5 is what you'll get. Make sure you carry out this integration in equation number 4 and you verify that equation number 5 is indeed what you get by integrating number 4. So what we have obtained here is that when you move a charge in an electric field, the equation becomes 1 over 4 pi epsilon naught, the product of the charges divided by R. I want you to take note that equation number 5 and the Coulomb's law, the difference is in the R. The Coulomb's law, the denominator is R squared. But here, the work done in moving between 2 points or moving the charge, moving a charge between 2 positions is obtained through the formula product of the charges over 4 pi epsilon naught over R. Again, I insist that the difference here is this is not R squared. This is just R. So this is the work done, and this is what we call the potential energy. Now, let's look at the electric potential, what is measured in volts. So we say if Q prime is a unit charge, that means the value is 1. The work done, work done, let me go back to equation number 5 here. So if Q prime is 1, when you substitute here 1 in Q prime, you will get the same expression of number 5, except that you'll only have 1 Q, and that is what you have here. And therefore, by the definition of potential, the potential V at a distance from a point charge Q in a medium epsilon naught is given by this. In other words, the potential is work done per unit charge. Equation number 5, this is work done. Work done divided by charge Q. One of the Q's disappears. And so the expression for potential has 1 Q and 1 R. Potential, electric potential, is defined when you're dealing with work done per unit charge. When you're dealing with a charge that is 1 unit, you get electric potential. So this is equation number 6 is electric potential. Equation number 5 is potential energy. All right, please take note of that. If you have a question, you can ask after you have finished watching the video. So in the next slide, we just emphasize what we have already discussed, which is the potential difference between 2 points in an electric field is equal to the work done in moving a unit positive charge from the point at the lower potential to that at a higher potential. So by now you should be able to see that when you are talking about potential or potential difference, you are talking about work done and unit charge. Don't forget that potential is work done per unit charge. Otherwise, if you don't say unit charge, then you are basically talking about potential energy. The unit of potential difference is volts. If the work done in causing 1 coulomb of electric charge to flow between 2 points is 1 joule, then the potential difference between the points is 1 volt. In other words, 1 volt is 1 joule over 1 coulomb. But the electric potential is work done per unit charge, and that is equation number 7, which is work done is charge times voltage. These equations that I'm putting in a green color, these are main equations which you should pick when you are dealing with a numerical problem. That's why I've highlighted them in green. So here W is work done, Q is charge, and V is the potential difference. Let's look at the next slide. Suppose that a charge positive Q is moved by a force F from some point A in an electric field of intensity E to another point B. Okay, that's we are supposing. Suppose also that the distance delta x from point A to point B is so small that the force can be considered constant between A and B. Then, if you suppose the two, then the work done by the force is basically, force times distance. That is the work done. The small work done delta W is force times the distance. It follows from the definition of electric field intensity. Okay, this is what we discussed last week, that electric field intensity E is what measures electric field lines. If the electric field lines, some electric field lines are strong, some are weak, but electric field lines is measured using electric field intensity, which is basically force per unit charge. So here we have the formula F is equals to minus EQ. The minus here is because the electric field lines, that is measured by E, is in the opposite direction to the dragging force. In other words, the force is moving against the electric field lines, and the two quantities are vectors. So the sign is very important. So the work is done against electric field influence. E and F are oppositely directed. That is why we have the negative. So keep in mind equation number 8 and this one of F is equals to EQ because we want to use them. So if the potential difference between A and B is dV, B at a higher potential than A, then we say from equation number 7 that work is QV. Let me just scroll back to equation number 7 just to remind us. Equation number 7 is here, where we defined the potential as work done per unit charge. So work done is Q times V. So let's go back to equation number 9. This is work done, delta W is equals to the charge times delta V. So this is picked straight from equation number 7. So then delta W from equation number 8 is force times distance. But what is force? Force is minus EQ. Okay, so this is what you have. On the right hand side, you simply have Q delta V. So you have formed an equation that you can cancel the Q, and when you cancel the Q's, you will have that the electric field intensity will be given by negative dV dx. In other words, if the electric field lines are uniform, the equation simply becomes V over x or V over d, where x or d is the distance. Equation number 11 is very important. Now, dV dx, this quantity equation number 11, is the rate of change of potential with distance at a point in electric field and is called the potential gradient. The negative sign shows that electric field is in opposite direction to the displacement. The electric field and the displacement. Remember, when you're dealing with vector quantities, direction is very important. So the negative sign here indicates that the electric field intensity and the displacement are in opposite directions. Okay, now equation number 12, like we have said, is for uniform electric field, where we can say that electric field intensity is voltage divided by distance. Last week, we defined electric field intensity as force per unit charge. Today, we are defining electric field intensity as voltage over the distance between the charges. So either of the two definitions can be used depending on what scenario you are dealing with. So take note again, the equations that I'm highlighting in green. All right, we are doing well. Let's look at some examples. Point charges of 3 times 10 power negative 9, this should be coulombs, are located at two vertices of an equilateral triangle of side 20 centimeters. How much work will be done to bring a test charge of 10 times 10 power negative 9 coulombs from infinity up to the third corner of the triangle? All right, so this is the figure here. You have 2 point charges, each is 3 times 10 power negative 9, and then you are being asked what will be the work done if you were to bring a third charge at the third corner of the equilateral triangle. So this is how you are supposed to do it. First and foremost, you locate the two charges at two corners of the triangle. So in this case, we have said the two charges Q1 and Q2 are placed at the corners A and B of the triangle. So you place them at the lower corners. In order to bring a test charge Q3 from infinity to the third corner C, the work done becomes, so this is what you do. Let me explain before we look at this slide. You bring the charge at point C. When you bring a charge at point C, the charge at point A will exert a force on C. The charge at B will exert a force on C. So because of that, you do it in bits. You begin with the charge at C, the charge at A. You get the work done. Remember, we already have the formula. Equation number, I think it was equation number 7. This equation number, no, sorry, not this one. The equation number 5, this, where work done is being given by product of the charges over 4 pi epsilon naught r. So in this question, what you do, you get the forces between charge at A, charge at C. You get the work done, then you keep it aside. Then you do the same, you get the work done between charge at C, charge at B. And then what you do, because work done is not a vector quantity, Work done is not a vector quantity, so it does not have direction. Whatever magnitude you get between A and C and B and C, you simply add, all right? You do normal addition because work done is not a vector quantity. But if it was force or electric field intensity, you will make sure you get resultant through vector method. So this is what happens. You get the work done between A and C, work done between B and C, and you add them. If you substitute the values correctly, you should get an answer that is 2.7 times 10 power negative 7. Please try this. Make sure you get this answer. If you don't get this answer, please get in touch with me and we can look at where the problem is. So again, we have come to the end of this lecture. The terms are a little bit confusing, but I want you to read a little bit extensively. Read different books that have different explanation so that you get to understand what is electric field intensity, what is electric potential, what is potential energy, and what are the formulas that are involved. Because the formulas are increasing by the day. So when you just pile them until the exam time, you will not naturalize the learning process of these things. These formulas require a lot of practice. All right. Yeah. So please, that is the only caution I can give you, because as we move ahead, we are going to encounter even more formulas. So that being said, next week we shall be discussing what we call capacitors or capacitance. Yeah, so I think I will record that lecture and send you the video just the same way we are doing this one. And after you have watched the video, I think you need to give me feedback. Yeah, whatever, or if there are questions in the contents of the lecture, feel free to let me know. If there are technical issues, maybe the audio, maybe the speed of how I'm talking, maybe I'm moving too slow, I need to increase my speed, please do let me know. If you need a lot of questions for practice, please do let me know. If you have questions that you have got from other sources and you want me to look at how you have done them, please, you're most welcome. Um, because at the end of the day, what we are doing is what will form part of your exams. So everything is important. All right. So I think let me not say beyond that. Yeah. See you next week. You'll get the link, um, YouTube link. I'm going to share it in the LMS system. Otherwise, have a nice evening or maybe nice afternoon, depending on when you are you are watching this video. And then let's meet next week. Bye bye.